Good afternoon. Hi, welcome to Infinity Learn by Sri Chaitanya. Right, today we are going to discuss INMO Indian National Maths Olympiad 2025 paper solutions. Yeah, dear students, what a paper it is. You see, you know the paper pattern and everything. There will be 6 questions in this. You might have written, I hope some of you who are watching have written the exam very well. Yeah, dear students, you see, we can say this is a non-traditional paper. There are not too many questions from geometry, too many questions from, combinatorics. You see, induction based questions. Such a different kind of question paper we got in 2025 INMO. Right, dear students, without any further ado, let us enter the paper discussion, dear students. Right, so point number 1, you see here, dear student, question 1 we shall go. You see, yeah, consider the sequence defined by A1 is 2 and A2. You see, dear students, given A1 is 2, A2 is 3, and there is a recurrence relation given. A2k plus 2 is given as 2 plus AK plus AK plus 1, as well A2k plus 1 is given as 2 plus twice of AK. So where k is greater than or equal to 1 and a positive integer, natural number, determine all positive integers n such that an by n is an integer. This is the question, my dear friends. So that means indirectly he has given a pattern, a sequence, and he is asking us to find all values of n for which an by n is an integer. That means an is divisible by n. First, to understand the pattern, my dear friends, we shall do one thing. Try to write the pattern. You see, A1 is nothing but 2, A2 is nothing but, dear students, it is 3. Now, you just use, to find A3, you can use this relation A2k plus 1, which is twice of, put k is equal to 1, twice of A1 plus 2. Double A1 plus 2, that is 4 you will get. Right, dear students? Then the next pattern would be here A4 you need to find. To find A4, here you have to put k is equal to 1, which is A1 plus A2 plus 2, that is 2 plus 3, 5. You see, my dear friends, you have to put k is equal to 1 for A4, that is A1 plus A2, 2 plus 3, 5, 5 plus 2, it is going to be 7, my dear friends. Yeah, here you see this question, this is A3, you have to put k is equal to 1, twice of A1 plus 2, that is 4 plus 2, this could be 6, dear students. Yeah, you can say this is 6. Yeah, this is 6, this is 7. In this way, dear students, you can just find the pattern of the numbers. You will get 6, 7, 8, 11. You see, the next number you will get 8, 11. After that, my dear friends, you have to get the 7th one. You will get 14, 15, 16, 17, 18, 21, 24. After that again, you will get 30, 31. This is the basic method. What we do is, first if you write the pattern, we can observe something so that we can try to find out mathematically. From this, dear students, you see A1 is divisible by 1, so here successful we are because an by n is an integer. A2, 3 is not divisible by 2, but whereas A3 is divisible by 3, successful. Then again, this is not divisible by 4, not by 5, not by 6, but 14. A7 is divisible by, you see, A1 successful, and again A3 successful, and again A7, and again this is going to be 15th term. These are the successful terms where an by n is an integer. In all the other cases, my dear friends, yeah, in all the other cases, we are not successful up to here. Now from this, is there any pattern in the numbers 1, 3, 7, 15? So if you take AK, my dear friends, you can say the numbers are like, you see, first observation is 2 power n minus 1 kind of, you see, 2 power 1 minus 1, 2 square minus 1, 2 cube minus 1, 2 power 4 minus 1. So dear students, from these I am getting certain observations. Observation number 1 is when a suffix is an odd number, you see 1, this is again 3, 5, you are getting even number. You see, this is even number. You know why? You see here, because twice of 1 plus ak, so a suffix odd is even, and second a suffix odd you just take like, so this is, I mean to say, even. When a suffix is even number, you just see a2 odd number, a4 odd number, a6 odd number. This is odd number. This is first observation, dear students. A suffix odd is even, a suffix even is odd. So undoubtedly this case there is some observation here. This is a n by n cannot be integer, because a even number is odd. Odd by even cannot be integer. So friends, among the successful cases there won't be any numbers like a suffix even numbers. So we need to search our successful cases here only. Fine, okay. And second observation is, my dear friends, here we need to determine the cases where this kind. This pattern I have observed, so I am going to prove second part is, dear students, like a suffix is, I mean to say, case 1 I am going to prove ak by k is 2 if k is like 2 power n minus 1 kind of, like this case. Third thing that I prove is ak by k is more than 1 and less than 2 when k not equal to 2 power n minus 1. If I could prove these 2 points, the problem is done, because all such numbers are nothing but of the format 2 power n minus 1 kind of natural numbers. Got it, dear students? So these are the 2 things we need to prove. So if suffix k is like 2 power n minus 1, it is integer, so successful. And other than cases, it is between 1 and 2 in the sense the division is not an integer, so not possible. That is the thing we are going to prove. How to prove this, my dear friends? For that, what I do is, you consider the case, dear students. Here let me write. So continuation of the first question, continuation. You see here, right, I mean to say, take, dear students, some k is 2 power n, I mean to say 2 power n minus 1 case, or you can take n is equal to 2 power k minus 1 kind of something you take. Now what I am, so my observation here is, you see, a1 is 2, a3 is 6, a5 is nothing but, you see, a7 is 14, a15 is 30, quite double. So my observation, my induction is, you see, dear students, I take like a suffix 2 power n minus 1 is nothing but 2 into 2 power n minus 1 is my observation for all n. Okay, how to prove this? Let me prove this by mathematical induction. Suppose if you put n is equal to 1, a1 is nothing but true, it is clearly true for n is equal to 1. Fine. Now assume this is true for n is equal to k for some natural number k. For some k belongs to n, suppose this is true, that means a 2 power k minus 1 is twice of 2 power k minus 1. Now I need to prove that this is true for a 2 power k plus 1 minus 1. Am I correct? So definitely this is going to be odd. The result here is, my dear friends, for odd suffixes, this is 2 into 1 plus ak. So this becomes 2 into 1 plus, you will get a, this calculation becomes 2 power k minus 1 by this illustration. Just now from this, my dear friend, this is nothing but 2 into 1 plus 2 power k plus 1 minus 2, which gives 2 into 2 power k plus 1 minus 1. You see, clearly this is correct. So by finite mathematical induction, I can say that this statement is true for all n. So I proved this by finite mathematical induction, dear students. Then that means, you see, ak by ak is 2. and hence I can say a 2 power n minus 1 by 2 power n minus 1 is equal to 2 is an integer. That means I can say that he is asking us to determine all positive integers n. So n is the kind 2 power lambda minus 1. For this is correct. The next, my dear friend, that means I have proved this case, and the question is, are there any other integers also satisfying this? Very clear that, my dear friends, other than these numbers, you observe here, clearly they are, see, 3 by 2 is more than 1, 7 by 4 is more than 1. So ak by k is clearly more than 1, clearly more than 1. The next, I want to prove less than 2. Clearly, I mean to say, my dear friends, here, I mean to say, so let me take here, let me do here, dear students, the third part. Suppose here a k is, you see, I mean to say, I want to prove a n by n is less than 2. That means a n is less than 2n I want to prove. Okay, fine, we will do very simple observation. This is a n by n is less than 2, or you can see here at least for a1, a2, a3 up to 15 you can observe, except these. I mean to say dear students, this is here for n is not, where n is not in the form of 2 power k minus 1. For such numbers I want to prove, dear students. For such numbers, just now we have seen, for such numbers this n value, this is going to be 2. All the other cases you observe here, this is a n by n, you see 7 by 4 less than 2, 8 by 5 less than 2, 11 by 6 less than 2, all the cases. At least you can say, my dear friends, this is true for at least m less than or equal to, you can say 10. I have observed up to 10 of the format 2k minus 1, right? So a n is clearly less than 2n for the numbers of the form 2k minus 1, at least up to 10. Suppose that maximum number is 10. Now I am going to prove for all such numbers by mathematical induction. I am going to prove that am is less than 2m for all m of this kind, 2k minus 1 kind of. How can you say? Clearly for m is equal to 1 it is correct, and suppose it is true for some m, you consider for a 2m plus 1. You see, you just consider by mathematical induction, you can say a m plus 1, you can say a 2m plus 1 is less than 2 into, you see, from this, my dear friends, you can say, yeah, 2 into 1 plus, because it is odd number, 1 plus am you can write by this definition. So when it is odd, you can write 2 into 1 plus m. But am is, you see, am is less than 2m. So you can write this is in fact equal to, so you can write less than 2 into 1 plus 2m. You see, if you bring 2m plus 1 to the denominator, a 2m plus 1 by 2m plus 1 is less than 2. So finally we say, dear students, this condition here, a 2m plus 1 by 2m plus 1 is less than 1, you can say, I mean less than 2. Okay, so clearly we are able to say that ak by k cannot be 2, cannot be more than 2, it is between 1 and 2, so it cannot be integer. So combination of these two, you can say, my dear friends, finally the numbers which can be written an by n or integer kind of numbers are all nothing but 2 power k minus 1, where k is some natural number, right? That is the solution for question number 1, dear students. You see question number 2. Yeah, here suppose n greater than or equal to 2 be a positive integer 1 to n. The integers 1 to n are written on a board. Okay, in a move, allies can pick up two integers written on the board which are different, such that a plus b is an even number, that means both even or both odd. Erase both a and b from the board and write the number, their average, a plus b by 2 on the board instead. Find all n, we have to find all such n for which allies can make a sequence of moves so that she ends up with only one number remaining on the board. Okay, so when n is equal to 3, so 1, 2, 3 are there, So you can replace 1 3 with 2 2 2, you cannot move further. So it is not a successful case, right? So that is the point, my dear friends. Hope you have understood the question. The question is, you take, if you choose some n, you have to take the first positive integers up to n. You take any two different numbers, replace those two numbers with their average. You have to take such a way that both even or both odd. Now if you keep on continuing the process, the n is said to be successful if you end up with a single digit, right? For example, if you take n is equal to 2, my dear friends, you are left with only 1 and 2, you cannot move further. So this is not a successful case. N is equal to 3 you take, that is 1 2 3, you can replace 1 3 with 2, so that you will get 2 2, you cannot move further, it is not a successful case. If you take n is equal to 4, dear friends, 1 2 3 4, which implies you can replace 1 3 with 2, you can say 2 2 4, you can replace 2 4 with 3. So T 2 3, you cannot move further, even n is equal to 4 is also not a successful case. You take n is equal to 5, my dear friends, n is equal to 5, yeah. So that means, let me write here 1 2 3 4 5, replace 3 5 with 4, so that 1 2 4 4, then again replace 2 4 with 3, 1 3 4, and replace 1 3 with 2 2 4, if you replace again you will get 3, my dear friends. That means, so n is equal to 5 is a successful case. So he is asking us to list out all such numbers n which are successful. N is equal to 5 is successful. If you take similarly n is equal to 6, it will not be successful. But you just take n is equal to 7, dear students, that is 1 2 3 4 5 6 7, right? So here, my dear friends, you just do with 5 and 7, you will get 1 2 3 4 6, this is 6, again 6 4 if you write 1 2 3 5 6, 3 5 if you replace 1 2 4 6, and 4 6 you can write 1 2 5, right? So once again, here you can do in a bit a different way to go to that conclusion. I mean to say, yeah, so you can write, so 1 2 4, once again you see, dear students, so 3 5 you can replace 4, then 2 4 you can replace with 3, this is 3. So 1 3 5 in the sense you will get a 2 2 5, 2 5 means you will get, this is 2 5 means you will you are going to get, yeah. So 2 and second one is 6, this is 6, not only 5, this is 6, 2 6, 2 6 means 4, you will end up with 4. So here, by observing a pattern, you can observe that if you take the numbers n 1 to n greater than or equal to 7 and odd number, if you take n is odd and greater than or equal to n, so the same pattern you can continue, you are going to get it to be, I mean to say, dear students, n minus 3. You will get here 7, you got 4, so n minus 3. That means if you take the odd natural numbers, n is odd, greater than or equal to 7, every time you can proceed in the same way, you will end with n minus 3. That is the first observation. The next, my dear friends, you take n plus 4, you just take first n plus 4 natural numbers, that means like m plus 4. Suppose n is equal to say m plus 4 you take n value, where n is odd, I mean to say n is odd and n greater than or equal to 9. So n is odd, that means m is odd, and m greater than or equal to 9 you take, suppose. In this case, what you observe is, you see, let me take like 1 2 3 4 and so on, m minus 2, or you can write m minus 1, m plus 1, m plus 2. Let me write here, dear students, yeah, so that you can observe a pattern here, we can generalize to find the answer, dear friends. So 1 2 3, and so on. You can take here, my dear friends, like say you can say like m, or this is m, m plus 1, m plus 2, m plus 3, m plus 4. You can take up to here m plus 4. See, what do you observe? You can replace these two with m plus 3. You will get m plus 3, m plus 3. So m plus 1, this is m, this is m minus 1. Again, if you can replace these two with m plus 2, m plus 2, m plus 3, m minus 1. Right, dear students? And again, you can replace these two with m plus 2, that is m minus 1, m plus 2, m plus 2. You just take m minus 2 also, right? So in this stage, my dear friends, if you take up to n minus 2, you will get here, you can do for these two, you will get m, and you will get m minus 1, m plus 2, right? So m and m plus 2, you are left with m, right? This is m plus 1 and m minus 1. For these two, you will get m. That means, my dear friends, that means you have used up to 1, 2, 3 and so on, m minus 3, you can say m minus 3, and you can take m will be left, my dear friends, right? Now, if m is great, so for these you have seen already, if you take n greater than or equal to 7 odd number, here you will get, what will you get? N minus 3 you will get, my dear friends. N minus 3 means you will get m here, right? M minus 3 you are going to get here. You see, if you use m minus 2, you are left with m minus 3, right? If it is m minus 3, dear students, you are going to get here n minus, you see, whatever number you got, n minus 3 means this is m minus 3 means you will get m minus 5. And you can say m, you see here m minus 1, this is n plus, I mean to say m plus, you will get m minus 3 means m minus 6 you will get. The average of these two, you will get m minus 3, which is going to be a single number. So if you take n like m plus 4, where n is greater than or equal to 9, because m minus 3 must be more than 7. In that case, I am using for all the remaining numbers here up to m minus 2. Since m minus 2, m is greater than or equal to 9 means m minus 2 is greater than or equal to 7, right? So in that case, 6 anyhow not successful. In that case, you are going to get it as m minus 3. M minus 3 here already, here minus 3 is there means available number, minus 3 means m minus 6, here m. So you will be getting m minus 3, a single number, successful. So I can say, my dear friends, with this observation, n is equal to 5 is one case, and all the other cases where m plus 4, m is odd number and m plus 4 greater than or equal to 9 cases, you are going to get successful attempts, dear students. Next, you see this question, dear student, geometry based. Suppose Euclid has a tool called splitter which can only do the following, I mean to say two types of operations. Given three non-collinear marked points x, y, z, it can draw the line which forms the interior angle bisector of angle x, y, z. Suppose, what a hypothetical case. Suppose Euclid is having only one device, that is called slider. So what? Splitter which can draw the angular bisector of the given angle and can mark the intersection point of two previously drawn non-parallel lines. That means if two lines are there, if they are intersecting, you can mark the point. Only these two tools are there. Now suppose Euclid is only given these non-collinear marked ABC. Prove that Euclid can use the splitter several times to draw the center of the circle passing through ABC. Here, dear students, let me write, suppose these are the points ABC be the triangle, okay. Here, dear students, you just draw, now you know angle BAC, internal angular bisector, you can draw. Here angle B also, angle C also you can draw. Suppose this point of concurrence is in center of triangle ABC, you know well, let it be I. The next, my dear friends, you just take the angular bisector of BAI. Suppose it cuts this angular bisector at x, my dear friends, at x. The next, my dear friends, you just take the angular bisector of XIB, this angular bisector, and angle ICB angular bisector you can take. Suppose they intersect at the point I1, my dear students. In the same way, if you produce this and you take this internal angular bisector, suppose they intersect at I2. Clearly, my dear friends, for the triangle BIC, you see, for this triangle BIC, this is nothing but exterior, X center opposite to C. This is nothing but X center opposite to B. Now, dear students, there is a result, I think you know well, for triangle, the result is for triangle ABC, if you take the X center opposite to B, X center opposite to A, say I2, I1, the points I1, I2, B, C are concyclic with diameter I1, I2. That is the result. Let me repeat. So, if you take X center opposite to B, I2 and IC, let me say here I1, okay, these 4 points are concyclic with the diameter I1, I2. So, there exists a circle passing through these 4 points, my dear friends. Yes. So, now suppose let me take that circle. Yeah, suppose this is the circle here. Suppose I1, I2 is the diameter, say BC are here. Now, you do one thing, I1B, I2 is one of the angles, okay. You take, of course it is the right angle triangle, you take its angular bisector. The result says that this bisects the arc I1, I2 at the midpoint. This point is, let it be P, nothing but the midpoint of the arc I1, I2. Of course, if you draw IC2 angle and if you join this I1C, I2, if you draw, it will also cut at the same point. So, P is the point which is exactly midway between I1 and I2 on the circle, my dear friends. Now, I can say, so I1P, I2, so since it is the midpoint, so this is an isosceles triangle. I1P, I2 is an isosceles triangle. So, if you draw the angular bisector of angle P in I1P, I2, this is angular bisector. But since it is isosceles triangle with base I1, I2, this angular bisector will act as perpendicular bisector. So, this is a circle, this is the diameter, you have done perpendicular bisector onto it. This is going to be the center of this circle, say O1, my dear friends, O1. Now, dear students, now you just join BO1, CO1. Clearly, these two are equal because radius, both are radii. Now, you just join BC, my dear friends. This is an isosceles triangle O1 BC. Now, if you draw this angular bisector, may not be the same line, this angular bisector, this bisects BC. So, this is going to be the perpendicular bisector of BC. Only through internal angular bisectors we are able to achieve the perpendicular bisector of BC. The same thing you do for AB. So, in triangle ABC, if you could achieve perpendicular bisector of BC, similarly AB, the point of intersection is going to be the circumcenter. In this way, you can arrive the conclusion, dear students. Right? So, it's very simple, just so beautiful. The problem is, I think, so beautiful. With the help of simple geometry results, with the help of only internal angular bisectors, we are able to locate the circumcenter of the triangle. What a wonderful question it is. Right. Next, dear students, you see this question number 4. Let n greater than or equal to 3 be a positive integer. Find the largest real number Tn as the function of n. So, Tn means it needn't be a number. As a function of n means the answer can be in terms of n, such that the inequality maximum of these is greater than or equal to Tn into maximum of these, my dear friends. Now, so to understand it clearly, this very important point holds for all real numbers a1, a2, an. This inequality must hold for all real numbers a1, a2, an. Such a maximum Tn you have to take, right? What is that Tn? Case 1, my dear friends, suppose n is even. If n is even, my dear friends, so since it is true for all a1, a2, an, let me choose a1 is 1, a2 is minus 1, a3 is 1, a4 is minus 1. In that way, an is minus 1. And substitute in this, because our numbers must satisfy this inequality. You will get a1 plus a2 will be 0. You will get the inequality like maximum of 0, 0, 0. Even a1 plus an is also 0, is greater than or equal to Tn into maximum of each modulus is 1, 1, 1, 1. So that means, my dear friends, 0 greater than or equal to Tn into 1, which is impossible unless Tn is 0, right? So Tn is, you see, Tn is 0, right? Yeah. So I can say, my dear friends, yeah, you can say here 0 is greater than or equal to Tn into 1 means Tn must be 0, dear students, right? So case 1, when n is equal to even, Tn is equal to 0 is the answer. Case 2, my dear friends, suppose n is odd. In that case, dear students, let me take here. Without loss of generality, suppose a1 or maximum of a1 is x, one of the numbers. The numbers you can take at random, the largest one, you can take a1 is x, right? So now, my dear friends, given, yeah, maximum of, suppose a1 plus a2, a2 plus a3 and so on, an plus an minus 1 plus an and an plus a1. Its maximum of all these, suppose a number capital M. Okay. Clearly, my dear friends, clearly, yeah. So a1 plus a2 now must be between minus m and m. Clear? So a1 is x, right? You just multiply with, dear students, you just subtract x, my dear friends. Clearly, you can say here, I can say you have to, you can say minus a2 you can add. So minus a2 can be added like x minus m, or you can also write a2 kind of you have to derive. So let me write, this is a1 is nothing but x minus m less than or equal to x plus a2 less than or equal to m. So that means minus x minus m less than or equal to a2 less than or equal to m minus x, right? Similarly, if you take for a3, my dear friends, you also get minus m less than or equal to a2 plus a3 is less than or equal to m. I want to subtract a2. You see, minus a2 means you can multiply here. So this is x minus m less than or equal to minus a2 less than or equal to x plus m. If you add these two, my dear friends, x minus 2m less than or equal to a3 less than or equal to x plus 2m. The same pattern you can do for a5, a7 also, because we are not interested in n is equal to even, we want n is equal to odd case only. For that, my dear friends, what we do is n is equal to odd case, you can observe the pattern like when n is odd, an is between x minus n minus 1 into m less than or equal to x plus n minus 1 into m you will get, right? After that, my dear friends, better you just write a1, you just add a1 also, so that a1 is x, so that 2x minus of n minus 1 into m less than or equal to, this is a1 plus an less than or equal to 2x plus n minus 1 into m. But interestingly, we know that a1 plus am's is maximum value, you know, a1 plus an should also be between minus m to m, right? Yeah, because This maximum is m. So from this, my dear friends, minus m is less than or equal to this. The conclusion is this minus m must be less than or equal to this 2x plus n minus 1 into m, from which you will get, yeah, so nm, right, nm less than or equal to 2x, so x greater than or equal to nm by 2. Similarly, this is less than or equal to m, you will get here 2x is less than or equal to, this is nm, you will get here, my dear friends, from this, this is minus m less than or equal to 2x plus this, and here you will get 2x is less than or equal to m, from which you will get minus x is, you can write x less than or equal to this, and minus x greater than or equal to nm by 2 you will get. Conclusion is mod x is less than or equal to nm by 2. But you see, the given inequation is given like this is maximum of this, that means m is greater than or equal to Tn into one of the maximums I have taken as x, my dear friends. So x must be less than or equal to, or you can say mod x must be less than or equal to m into 1 by Tn you have to get. But we got here like m into n by 2. So this one n by 2 will act as 1 by Tn will act as n by 2. Therefore, Tn will be 2 by n, my dear friends. So the conclusion is this inequality holds when if n is even, Tn value is 0, absolutely. If n is odd, Tn value is going to be 2 by n, right, dear students? Next. So this question, you see, dear students, yeah, greedy goblin grip has a regular 2000 gun whose every vertex has a single coin. In a move, he chooses a vertex, removes one coin each from the two adjacent vertices and adds one to the chosen vertex, keeping the remaining coin for himself. Greedy man. He can only make such a move if both adjacent vertices have at least one coin. Okay, and grip hook stops only when he cannot make any further moves. What is the maximum and minimum number of coins that could have been collected, right? You see, dear students, a 2000 gun is there. Suppose this is 1, 2, 3, 4, 5, yeah, 1997, 1998, 1999, 2000. Suppose the vertices of a polygon, of course I have drawn like a circle, let it be. Now he starts, I have to find the maximum amount he can collect, the minimum amount he can collect. Right, dear students, for the maximum let us start. So now everybody are having one coin, right, you see. So he moves one coin, see, he removes one coin from each from the two adjacent vertices and adds one coin to the chosen vertex, keeping the remaining coin with himself. You see, now everybody are having one coin. Let us start from here, dear students. Right. Suppose he takes coin from 2002, they are having 0, 0 now. He collected 2 now. He retains 1 with him and he gives 1 to this fellow. So this fellow will be having 2 here. Okay. Now dear students, I think you got my point. You see, once again, you see he has taken, I start with 1. So he takes one coin from 2000, one coin from 2 and collects 2. He takes 1, he put 1 there. Now he goes to 2. He may be not having coins, no problem, but 1 is having coins, 3 is having coins. So he collects 1 coin from 1 and 1 coin from 3, he is having 2. He gives 1 to 2 and he gets 1. You see, 2 moves has happened, he gained 2 coins. The next step, the same way. So now 3 is not having coin, but 4 is having 1 coin. So from 3, he collects 1 coin from 2 and 1 coin from 4, so that he will get 2. He retains 1 with 3, 4 will become 0. this becomes 0 and he gains 1. In every move he is getting 1 coin. You see, started with 1, so finally 1 is having 1, you see, clear dear students. So like this he will be moving for every step, you see, in every step. Suppose at step number 3, 3 is getting 1, 4 is getting 0, that is the observation. At step number 1997, 1998, you will get this fellow will get 0, this fellow will be 1. This anyhow had 1. So right my dear friends, so like that you will get 1997. After that the next step would be at 1999 he can collect, you see, 1998 he can collect one more step here, so that you will get 1 1 and you will be left with 0 here. So all together if you continue this process you will get 1998 maximum number of coins. With 1, with 2, with 3, you see he got every coin with 1, 2, 3 and so on. He can go up to 1998 my dear friends, because this side will be 0, this side will be 1. So 0 will be there. So 1998 also he can collect, so that this will be the stage, the 2 zeros will be 1999 and 2000. So in this case maximum case is 1998 my dear friends. The second thing dear students I can say, so for the minimum case take the same 2000 gone, 1, 2, 3, 4, 5, 6, 7, 8 and so on. This is 2000, 1999, 1998, 1997, like this. Now minimum number he has to take. Start with 1. He has taken 1 coin from 2000, 1 coin from 2 and he got 2. So he will retain, he will give 1 to this and he takes 1 coin. Fine. So with this move he got 1. Next step, so rather starting with 2, he cannot start with 3 also, because 2 is not having, because adjacent members must have coins. So don't start with 2, you cannot start with 3, start with 4. At 4 you collect 1 coin from 3, 1 coin from 5, he will get 2 of these, he gives 1 to 4 and he retains 1 coin, 2. After that he cannot do at 5, because I want minimum case, I don't want to go to 5. 6 I don't want to go, you see, he stops until then, he has to continue until the game stops. So 6 he cannot collect, 7 he can collect my dear friends. 7 he can collect in the sense, here he takes 1, here he takes 1, he will put 1 here, already 1 is there, he will give 1, he takes 1. That means, you see here, what are the successful cases? At 1 successful, again at 4 successful, then again 7, 10, 13, there is a pattern. It's an AP with first term 1 and common difference 3. So A plus n minus 1 into D, yeah, this can be all the numbers of the kind 3n plus 1 my dear friends, 3n plus 1. So of these 1999 is going to be 3n plus 1. So n is going to be, you see, 666 plus 1, 667. After approaching this case, there is one more possibility, maybe accordingly the answer will be 667 or 668 kind of. Okay. So this is the pattern you can go to minimize the score, right dear students. Then next, we can say the last question. Yeah. You see suppose B greater, you see the formation of the sentence. For B greater than or equal to 2 be a positive integer, Anu has an infinite collection of notes with exactly B minus 1 copies of a note of worth B power k minus 1 rupees for every integer k greater than or equal to 1. A positive integer n is called payable if Anu can pay exactly n square plus 1 rupees by using some collection of her notes. Okay. Prove that if there is a payable number, if there exists such payable number, we have to prove that there will be infinitely such payable numbers. Right. You see, what is the meaning of this? You see, suppose B is equal to 2. What is the meaning of this? Anu will have infinite collection of notes with exactly how many copies? 1 copy or one note of worth 2 power k minus 1 rupees. That means k can be any natural number. 2 minus 1, 1 rupee, 1 copy of 1 rupee, and 1 copy of, you see, 2 square minus 1, 3 rupees, and next 2 cube, 8, 7 rupees, and like this. These denominations are infinite, but 1 copy only. You will get, if you take b is equal to 2, that means they will have 1 rupee coin, 1 3 rupee coin, 1 note, 1 7 rupee note. This number is fixed, but this goes indefinitely. Suppose if you take b is equal to 3, the meaning is this: b minus 1 means 2 copies of b is 3. 3 power 1 minus 1, 2 rupees. 3 square minus 1, 8 rupees. 3 cube minus 1, 27 rupees. That is a meaning. Like that. Okay. Right, my dear friends. In this case, he is asking us, so when can we call a particular number is payable n? It must be able to, it should be, the denomination sum should be like n square minus 1. Friends, suppose lambda is a payable number. That means I can say lambda is a payable in the sense there must exist the sum of denominations for some k. You see, suppose we can write what is the sum amount, these many notes of denomination, worth is this. You see, you can write like pi into, you can write like b power k, right, my dear friends. You can write b power I, you can write b power I minus 1, where I is equal to 1 to n, it must be like lambda square plus 1. Suppose lambda is a payable number, that means this total sum of lambda square plus 1 is nothing but combination of, this is the worth of the notes, and this pi can be any number, like it can be 0, 1, 2, 3 and so on. You can write up to, you can say, my dear friends, b minus 1. There will be only b minus 1 notes are possible. Some combination, pi can be any number. But irrespective of pi, I can say that the sum is divisible by b minus 1. Am I correct, friends? Can I say that lambda square plus 1 is congruent to, because x power n minus 1 is always divisible by x minus y if n is a natural number. B is divisible in the sense is congruent to 0 mod b minus 1. That means, my dear friends, lambda square is congruent to minus 1 mod b minus 1. Am I correct? Say this is step 1. So I mean to prove that there exist infinitely such payable numbers. So let me take, my dear friends, some k is equal to m into b minus 1 plus 1. Right? Let me take, my dear friends, k is m into b minus 1 plus 1. Let it be k. You just consider, my dear friends, k square. K square is nothing but m square into b minus 1 whole square plus 2m into b minus 1 plus 1. Am I correct? Clearly, this k square, if you divide with b minus 1, remainder is 1. K square is congruent to 1 mod b minus 1. Already we got lambda square is congruent to minus 1 mod b minus 1. So lambda square, this is a given number. Lambda square is congruent to minus 1 mod b minus 1. So this is a number I have constructed because b is given. For a given b, m is my choice. I can take any m. So now just consider k square lambda square, which is congruent to minus 1 mod b minus 1. That means k lambda square plus 1 is congruent to 0 mod b minus 1. What does it mean? That means k lambda is also a payable number, right? It means k lambda is also a payable number. That means if you are given a payable number lambda, I am forming a new number k, which is m into b minus 1 plus 1, such that k into lambda is also a payable number. So m, you can run any number. So definitely you can say that there exist infinitely many payable numbers. Right, dear students? That's all about the solutions related to INMO 2025. The cutoff mark, 17 marks almost for each question. So the cutoff mark somebody is asking, it can be around question number 5, 6 are comparatively easy, and you see out of the 6 questions, first question and many students tried, and you can say fourth question also they have arrived. I can say almost it could be around out of 1 or 2 it may reach up to 50, 55 like that, my dear friends. Maybe some partial marks are allowed like that. At least I guess you need to answer 3 questions. So that's all, dear students. So stay tuned to Infinity Learn by Sri Chaitanya for further updates. Okay, bye.